Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. So I want to discuss with you this article that appeared on the online magazine LifeScience.com as published in the journal Nature. And basically, scroll up here a little bit, Antarctica could melt irreversibly due to climate change study warned. The change will take thousands of years, but we only have a century to stop it. Thousands of years is being optimistic, I hate to say. But, so let's go through a quick synopsis of what they're saying here. The simulation here shows Antarctica totally stripped of ice. In other words, this is what it would look like if there was no more ice at all. So they have, for example, the Wilkes Basin, Amory Island, and a whole bunch of other places, Ross Island, for example. If global warming is allowed to continue unchecked, Antarctica will soon pass a point of no return that could reduce the continent to a barren, ice-free mass for the first time in more than 30 million years, according to a new study published September 23rd in the journal Nature. Antarctica is basically our ultimate heritage from an earlier time in Earth's history. It's been around for roughly 34 million years, said co-author Anders Lieberman, a researcher at the Potsdam Institute for Climate Impact Research, commonly called PIK, in Germany. And I have shared with you the findings of many researchers out of PIK, leading along with BAS in the UK, the British Antarctic Survey folks there. They're doing some excellent work involving issues with Antarctica. Now simulations show that once it's melted, it does not regrow to its initial state until temperatures go back to pre-industrial levels, which is highly unlikely. In other words, what we lose of Antarctica now is lost forever. They actually have a term for that, which I will share with you in a bit. Now, keep in mind, Thwaites and Pine Island Glacier are especially vulnerable. And if Thwaites lets go, and Pine Island is probably going to follow right behind it. And that's going to be very disastrous, because then that could basically destabilize most of the ice sheets on the continent. And don't forget, a lot of the ice sheets are a mile or 2 miles thick. So they ran computer simulations to model how Antarctica will look thousands of years from now, depending on how high average global temperatures rise in response to modern greenhouse gas emissions. They found if average temperatures rise 7.2 degrees Fahrenheit, that's 4 degrees C, above pre-industrial levels for any sustained period of time, much of the ice in West Antarctica will crumble, resulting in 21 feet or 6.5 meters of global sea level rise. That would take out cities like New York, Tokyo, London, the Maldives, a whole bunch of places would be underwater. This scenario could be a reality within decades. A global average temperature rise of 5 C is currently considered a worst-case warming scenario if things continue, according to IPCC. Well, here we go again. I'm going to piss on the IPCC. They like to underestimate. Recall that I just did a video segment saying lessons from the early Eocene. And basically some researchers there are finding that as CO2 levels keep rising up, we could see increases in temperature of 9 Celsius by 2100. That's more than halfway towards the what's called a PETM, the Paleocene, Eocene thermal maximum. More than halfway towards that. And these models are basically saying CO2 levels keep rising the way they are rising. 9C is going to be more of the mainstream estimation, not an extreme estimation. So right now, the same 4 or 5 is kind of, with the new modeling that's coming in from other researchers, is a low ball in my assessment. I looked at the analyses that where they did they said 9C, and I looked at how the assumptions they made in the model, looking at the CO2 level. They looked for clues in data from the past. 7 to 9C is probably what's going to happen by 2100. That's going to have devastating consequences. So they're assuming in this study here, they're assuming 4C, and let's say take thousands of years. If it's 7 to 9C, it's not going to take thousands of years. It's going to take centuries, and that stuff is going to melt. You're going to have the collapse much faster. If those IPCC projections are off, things could get much, much worse, the authors of the new study found. Should global temperatures rise between 6 to 9C, what I was just saying, above pre-industrial levels for any sustained period of time over the coming millennia, that's optimistic, try the coming century, more than 70% of Antarctica's present-day ice will be lost irreversibly. If temperatures rise by 10C, 18F, the continent is basically going to be no ice, sans ice. Should the continent lose all of its ice, global sea levels will rise by nearly 58 meters. Toss in Greenland's ice loss, and you can be topping 70, 75 meters. That will inundate lots of the continents and lots of the islands. Indonesia, the Hawaiian Islands, right? The Indies, West Indies, whatever. Be underwater. Basically, any places that have an elevation less than 200, 250 feet or so, you will have a beachfront property. So let's see if we can play this short little video here. Temperatures could increase 7 to 9C by 2100. Well, we just saw in the simulation with 10 to 11C will do to the ice in Antarctica eventually. 7 to 9, we're basically 3/4 of the way to that projected scenario. So, and don't forget, you have to take into account the thermal inertia in the system, and that the warming will, because of thermal inertia, will continue. We've already set into place so many positive feedback loops, the thawing out of the permafrost, methane being released, and other ongoings. So we're not going to meet that goal. I'm sad to report. So, as we saw in that video, this is a simulation modeling of what will happen to Antarctica if temperatures were to increase to 9, 10, 11 degrees C above pre-industrial revolution temperature levels. Now, will that melting take place all at once? No. There's approximately a 100,000 to 150,000 year lag because, the specific heat of water and so forth. But it still will raise sea levels by some 58 meters, as we mentioned earlier. Couple that in with Greenland's ice loss, and that could contribute another 12 to 17 meters. So you're looking at 70 to 75 meters higher sea levels. That's, of course, is going to impact the continents and the coastline. Basically, anything that, is 300, about 100 meters or so less. So you have large sheets on the continent itself. Then you have part of the sheets then extend, basically cantilevered out over the ocean. The point, or more of a line, because it goes up it follows, is what's called the grounding line. On one side of the grounding line, the ice is on the rocks. On the other side, it's cantilevered over the ocean. That's what's vulnerable breaking off. So you got the melting from the warming air above. Now the oceanic waters are warming up. So you got the warm water coming in from the underside, warming the ice from underneath. So those two are going to meet in the middle, and they snap off. And that's what you see about the ice shelves breaking off and so on. Then the current picks them up, etc. Well, what that does is that frees up the ice behind it. So now more of the land ice will start sliding down. So that what was once over the sea is now broken off. That the ice that was on the one side of the grounding line will now proceed over the other side of the grounding line. So that, again, more ice will now be cantilevered over the sea, and the whole process repeats. And this is how the ice can actually disappear in quite dramatic fashion. So that, and this will set up a positive feedback loop where this increases and increases. So that's something that they're expressing concern over. And the video was talking about, 2 degree Fahrenheit. Well, that's about 1.5 C or so, 2.7, what have you. We're not going to keep it to 1.5 C or less, which is according to the Paris Accord. We're already about 1.3, 1.4, depending who you look at. So now can we keep it to under 2 degrees C? Well, modeling is saying that by somewhere between 2030 and 2040, we'll probably hit that. I did that video segment where I talk about lessons from the early Eocene, where some modeling now saying that by 2100, warming could go from anywhere from 7 to 9 C. Well, this video simulation took it to 10, 11 C, almost all the way there. And if you notice, if you go back and look at that simulation, you see how the melt rate accelerated as the temperature increased more and more. That's part of the exponential melt rate, which we're now seeing. Not linear, it's exponential. Melt rates increasing exponentially. Temperature increases are exponentially. Part of the feedback mechanisms looping in. So between this video, where I'm showing you the model is happening to, potentially happening to the Antarctic ice sheet, along with my Eocene video, you can see now some of the risks, the concerns that are out there. We're really warming things up, and we're going to just set a whole bunch of stuff in motion. So that's kind of the idea of what this research was about. Now, let me actually share with you. I'm not going to go into great detail with this because it's lengthy. It's an actual scientific paper. This is the paper that what I just shared with you is based on. Let me get this thing to cooperate. There we go. The Hysteresis of the Antarctic Ice Sheet. And here are the authors. Julius Garve, Torsten Albrecht, Anders Lieberman, Jonathan Donges, Ricarda Winkelmann. Okay, and I mentioned Anders Lieberman earlier. If you are interested, okay, you can pause the video, and here is your URL right here, https://doi.org, etc., etc. You can type that into another tab, and it'll pull this up. This is in PDF form. Now, these authors were kind enough to have this available to us. They were kind enough to do that in its full form. Lots of times, many times, it isn't. I often receive comments like, Jen, please include the URLs for these papers that you discuss, from the peer-reviewed journals. And I don't, because of the cost. Okay, to access these papers requires a subscription, and the subscriptions are not cheap. They're typically 3 digits before the decimal point. You know, $100, 120, 150, 170. You know, they're expensive, and people are not going to fork out that kind of money. You know, it's so that's the reason. I think when I first started this channel like some years ago, I did, and people then found out, you know, and they basically accused me of trying to do a kickback with some damn thing. So I stopped. I just don't do it because of it is expensive, and people just don't have that kind of money. So, which is why I do my best to try to explain to you, give you the nuts and bolts, the essence of the paper and what it means. And I consider that my job to take something like this and distill it down. So, for the non-professional scientists, something that people can understand. And I know my audience is intelligent enough to understand what we're trying to do here on this channel. So here's an abstract. An abstract is a summation of the research. A good abstract will pull the reader in. A bad abstract, the reader will go on. Usually an abstract, the good ones that I've seen, these are the ones I try to write myself, is a summation of what the study was all about, the hypothesis being examined or whatever was being examined, and a synopsis of the findings. Boom. There it is. From there, you go into the introduction. The introduction you can think of as your literature review, where you mention research related to what the study is looking at, what's been done in the past. So you give the citations of the studies, the authors, the year, that kind of stuff. So you're given the big picture, if you will. A lot of people think the abstract's the hardest to write because you have to really make a good synopsis of it, and it is difficult to write a good abstract. I've always found the introduction, at least to be the biggest pain in the ass to write, because this means you got to do literature review. So you're pouring through papers and stuff like that. And then you're going to come to the methodology section, which is straightforward. You're basically explaining what you did. Perhaps these are my sampling stations. We might show a map of the sampling station. These are the methods we did. If there's any mathematical equations that are going to be used, you develop them, derive them in that section. You talk about what analyses you're going to be using, statistical differential equations, whatever it may be. You present all that. So then, so basically the whole point of the methodology section is that anyone reading your paper would be able to reproduce what you did, at least the methods, procedures, that kind of stuff. That's the whole point of science, is to share what you've done. Others can do it, maybe replicate your work, or at least have an understanding of what you did and apply your techniques to their studies. The next section is the results section. And that's basically where you present your results, something like this figure here. You present maybe graphs or tables, statistical analyses summed up, other figures and so forth. You present a lot of diagrams, a lot of stuff like this that you see here. And you then have a discussion of what it shows, what you found, your results. You're going to give statistical numbers. For example, the mean was this, the confidence intervals was this, it's so on and so forth. Dry reading, but that you're presenting a summation of your results, your data. This is where you're presenting your data in the results section. That's what you're doing. So usually the methods and the results are the first sections that are written. As I said, mentioned before, the introduction is tedious because you're doing your literature review. Often, I've always found it the biggest pain in the ass to write. Good abstracts are hard to write. I didn't mind writing the abstracts, but that was like, cool, this is what I did. Doing the intro, yeah, it was pain. Then you come to the discussion. Now, oftentimes, the discussion, you're going to end up rehashing some of the material that you presented in the intro, but you put it in the spin of in context to your study, the study you just did. So you present things like, we found our findings uh, support the findings of so and so. Our findings verify the previous studies. Our findings differ in however they differ. So you discuss everything. You put it all in context, and you basically saying, okay, so now you put it in context. Here are the implications of our findings and what it means. And you try to wrap it up. Sometimes there's a separate conclusion. Oftentimes you just see discussion and conclusion. We do the wrap up within. It depends on the format of the journal you're targeting your paper for. So that's kind of synopsis goes into a scientific paper. Now, as to this here, as I said, you pause the video, copy over the type into another tab the URL, and then you can pull up this paper and spend your time doing a deep dive on it. This is a very this graph is kind of the crux of the entire paper. If you look at this here, if you're moving from the lower right to the upper left, and you see this little line says regrowth, that means this would be the ice reforming, those freezing back up, the water freezing back up. If you're going from the upper left to the lower right, that is retreat, or another way of saying ice melting. This blue shaded area, that's, they talk about the two branches of the hysteresis, but the best way that I can sum up what is meant by hysteresis for you folks is as follows. If you look at how much ice has been lost to melting since the onset of the Industrial Revolution, 1.3, 1.4 C right now. So if you look at how much ice has been lost since the onset of the Industrial Revolution, how much the planet has warmed. If you were to somehow able to cool the planet back down to those pre-industrial revolution levels, in other words, cool it back down 1.3, 1.4 C, not all of that meltwater will refreeze back into ice. That difference is hysteresis. That's really the best way that I can explain, that to you. And I think that's a concept you guys can visualize and get a hold of. I hope. And that's what they're basically looking at. And the further in time you go and the warmer you get things going here, like look at the mean global temperature, the warmer you get things going here, the more difficult it will be to refreeze it, or more difficult to cool it back down, and the faster would go that rate. Right? This is showing ice levels just bombing off here. So that's the essence of what hysteresis is. The difference between the ice lost through the melting now, and if you were able to cool the planet back down, not all of it would freeze back up. Not all that meltwater freeze back up. That difference is hysteresis. So I'll leave it there. I said, here's the study. They got a whole bunch of various graphs and so on. I could easily do a 2-hour video on this paper alone. It's very detailed. And you see here, discussion and conclusion. Ocean-induced versus atmosphere-induced changes. This is part of the results section. Sometimes you see nowadays results with presenting the results and a little bit of discussion tossed in there. Whatever. But here you get discussion and conclusions. And then, of course, all the references. Right? This is all the literature that has been cited in the presentation. This particular publication, they cited 52 other papers. I've seen 20, I've seen 200. Okay. So, yep, here's a bona fide peer-reviewed scientific paper. It's like stills from that animation video I showed you earlier. You can see more and more land being exposed as the ice melts away. That increases rapidly. So if you're interested in doing a deep dive on this this article, and leave it at that. Thank you for your time, and I'm hoping that between this paper and this video and the video I did on the lessons from the early Eocene, you kind of see the risks that the big ice sheets, the threat that they're under, and what it would mean to the planet. And when you have the sea level rising like this, it's not just the coast that will, you use coastline there, so you have high sea level. You got a river basin, sea level is going to flow right up the river basins. So places like the Mississippi, the Amazon will be flooded with the invading sea, and substantially flooded. Just remember, during the Jurassic, the Triassic into the Jurassic, North America was nearly split in two by an inland sea. Go to New Mexico, you can find fossils of marine organisms there. New Mexico used to be beachfront property. So that's the other. So basically, you're going to lose a lot of land to rising sea levels, and that will, now granted, the melting is going to take place over 100,000 years or so, but we're still going to have the immediate melting now. We're already seeing sea levels rise. That's going to displace more people, going to create climate refugees, and the infiltration into the aquifers, turning potable water into brackish water, which is not potable anymore. There are issues coming down the pipe. Sea levels may not rise 75 meters in our lifetime, but they could rise several meters in definitely by the end of the century, which will be a impactful and a bad impact. So this is serious stuff. Again, thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.